staff response and engineering design, and basically developing the concept of the pre-warning time, the time in which there's a delay before people can actually commence the evacuation. And as trailed by a person next door, this is this picture is of the fire, and I just think it's an interesting picture because these are the footprints left in the soot gathered on the floor, and these seemingly random seemingly random behaviours that were exhibited, but actually we could actually understand some of the complex behaviours during this incident, even though it's seemingly complex, random and undecipherable. So, oftentimes in the procedure there are numerous legitimate procedural responses required from different, including different staff actions and decisions. So it may be that there are legitimate reasons for staff to intervene, to make decisions and to delay the initial response of the evacuating population. However, each of these actions, irrespective of whether they're legitimate or not, takes time. This time may delay notification of the target population, the population that you want to evacuate, and then they may also delay their time to reach safety. Now, oftentimes this delay, this pre-warning delay, the time that staff delay the raising of the general alarm, is often accounted for in engineering design by the inclusion of what's called a fail-safe switch. So the alarm system is activated, a signal is sent to a control room, and then if that signal is not addressed within a period of time, say 2 minutes, then an automatic general alarm can be sounded. However, oftentimes a member of staff can just click a button to notify they've recognised the private alarm signal, and then may delay a long period of time, but the alarm has actually been recognised. So oftentimes issues arise when these fail-safe switches are overridden by members of staff. Often there are errors, misunderstanding and perception issues, both in terms of the members of staff and in terms of the evacuating population. Indeed, perhaps a subtitle of this presentation should actually be "Staff are Human Too." They have to go through the same cognitive processes, the same decision-making processes, albeit at potentially at an accelerated rate because of their training and their expertise. But they still have to make decisions and process information. Now, more importantly perhaps, this potential delay should be recognised and better accounted for in the engineering process. Often this is not the case, and as Professor Purser noted earlier, this extended notification period, the time from detection to when a general alarm is actually enacted, can be a significant amount of time, delaying the evacuating population reaching a point of safety. Now, it's broadly recognised, I think, and Professor Purser showed this diagram earlier, it's broadly recognised that the time from when an alarm is sounded, a general alarm, to the time when the population eventually begins to move is a significant portion, it's an important amount of time that can often dominate the amount of time for a population to reach safety. However, from my experience in doing third-party reviews of engineering analysis, this time, the time from detection to alarm is often either completely ignored or is accounted for by manufacturers' data. It could be a single 30 seconds, a minute, a very small amount of time depending on the technical time at which the signal is sent internally. So oftentimes we account for the pre-evacuation time and the overall evacuation time using complex simulation tools or engineering calculations, but we account for the detection time using manufacturer's guidance. So if a certain temperature is reached or a smoke density is reached, then the alarm will sound. And then notification time, well, the automatic time is assumed given that a fire has been detected, rather than any procedural actions that are required within that structure. So as Dave mentioned earlier, he's begun to address this, or at least account for or recognise the situation in the UK code and in the Mirror codes, where he's identified different types of alarm systems based on the manner in which they detect the original incident and then the manner in which the alarm signal is sent, whether it's a general alarm signal, a private alarm system, or whether confirmation is required. Now, the original assumptions regarding detection and notification are sort of broadly appropriate in the first case, where an alarm is detected, it's complete coverage, a complete detection system, is detected quickly, and then a signal is automatically sent and a general alarm is immediately distributed. So in that case, the manufacturer's assumptions may broadly be accepted. However, when there's any staff activity required, when there's any confirmation required, or when there's an initial detection is by a member of staff, then the human process intervenes. And we can't then necessarily assume that the manufacturer's guidance is appropriate. In these situations, this time here, time to notification may be much greater than we had previously assumed. Now, in this paper, what we're doing is coming up with a crude way of estimating or accounting for this notification time, given the procedure that's in place. I'm not attempting to predict staff actions on an individual level, but given that you know a certain procedure is in place, and the method of sensing an incident, and the method that is intended when the alarm is distributed, you can then account for the number of staff decisions that are required as a bare minimum. So, given that you can do that, you can at least get a broad estimate of the time, the expected delay time before the general alarm is even enacted, and then the population begins to evacuate. So I thought a couple of illustrative examples would be useful here to demonstrate the types of delays that I'm talking about. This is a fire identified by Sekizawa et al. In the Nagasaki store in Japan in 1990. A fire developed in the sales floor, on the fourth floor of the structure, so in this red area here. In the building at the time, there was 130 plus people. Now this fire spread throughout the floor in 10 minutes. It started on the fourth floor and entered the third and fifth floors by the stairs and lift shafts, and a delayed response occurred that prevented the population on the fifth floor evacuating. These were forced to take refuge, and in the end, a large number of people succumbed to the incident. 15 people died. All of them were originally above the floor, the floor on which the fire started. And let me go through this. So, a fire was detected at 12:32 on floor 4. A signal from a detector was sent to a command and control office on the 5th floor. Now, and this then contacted the officer on floor 4 to confirm that it was a real fire. So there was a confirmation step. This was confirmed, and then the officer on floor 4 then commenced the evacuation of that floor, the fire floor. The officer on floor 5 in the command centre attempted to contact another member of staff, a senior member of staff, to get guidance. And he did this by a coded message. Nothing happened up until 12:35. So we're talking about a relatively short period of time, 3 minutes. By this time, thin smoke was then seen on the 5th floor. Another 3 minutes elapsed, and then at 12:38, a general evacuation announcement was made. However, evacuation of staff on floor 5 commenced but failed. And basically 75% of the people initially starting on that floor succumbed. Now, here we're in the King's Cross underground fire that Professor Purser talked